Hey everybody, welcome to a new unit. Unit 5, Earth's Geologic History. So in this unit, we're going to touch on a lot of subjects. One of them is today, how the Earth formed, the early Earth. So let's get things started. We got some nice photographs here. Can you guess what that one on the left is? If you guessed a dinosaur footprint, you're right. That's a photograph I took out in the deserts of Utah. The bottom picture, Meteor Crater, Arizona. And the right-hand picture, yep, that's a T-Rex skull. So first of all, before all that happened, let's go back to the very beginnings of Earth, the Precambrian Earth. Earth, we know, formed about 4.6 billion years ago. Ba means billion in my class, and ma, you can probably guess, means million. So both terrestrial and extraterrestrial evidence, that means both Earth-based evidence and evidence from off the Earth, like the moon, has revealed the following. First off, the Earth is 4.6 billion years old. Second, we know that the Earth formed from a primordial nebula, a hot dust, debris, and gas cloud that orbited our early sun. We can actually see this with other stars far away using telescopes. And so we know that this process is a normal process for stars in our galaxy and probably other galaxies too. So as our solar system, our early solar system cooled off, the elements condensed. They cooled off and formed, what they are today into solid planets, the 4 inner planets. And these layers differentiated, which we're going to get to in a few slides. Evidence for this, well, some of the evidence came from these really tough crystals of zircon, and we were able to date these things back to 4.2 billion years old on the Earth from the last I read about, and on the moon about 4.6 billion. So we know that if these things are tough, they can exist through all the weathering that the Earth is throwing at them, and they know that they're about this age. That pretty much narrows it down to how old the Earth is. So the nebula hypothesis, how our solar system and sun and planets came to be. We start first with the solar nebula. These can be formed from the explosions of, for instance, first generation stars, the earlier stars in the formation of the galaxy. And as these stars supernova and spread their guts across space, they can be contracted by gravity, igniting a new star, in this case our sun. And as the material that's orbiting our new sun starts to condense, that means cool off, it forms into these stable orbits. It kind of falls into place, and you'll see the rings there around that bright spot in the middle, which is our early sun. Collisions within these debris rings start to form our protoplanets, the planets before they're actually planets. And as they start to congregate together into larger chunks, they draw in more objects, and eventually that ends up with Earth orbiting the sun along with the other inner planets, and then of course the outer planets, which are gaseous. The early Earth differentiated, and this is because the early Earth was hot, it was liquid, and gravity, remember, is centered around the center of our mass, which is the core of the Earth. And so the most dense objects, the most dense elements ended up in the middle of the Earth, and less dense as you move your way out. So the surface of the Earth, as we learned back in the rock unit and in plate tectonics, is made of the lower density rocks, like granite. So everything differentiates by density, and you really should know that. The term differentiation and the fact that differentiation occurs by differences in density. So some conditions. What was it like if we were to take a time machine, come back to early Earth? Well, first off, lots of meteorites bombarding the Earth. It wasn't stable at all. Things still weren't finished yet, forming the planets. Perhaps no moon yet until maybe a Mars-sized object collides with the Earth, blows a piece of the Earth off, forming the moon. No life yet either. And the energy on the Earth, it was a really hot place, comes from the sun, from radioactive minerals that were decaying inside the Earth and the rocks, and gravitational contraction, which is just, it's actually forming a planet. Gravity's pulling everything the denser materials towards the core, and the friction creates energy, heat. Now, over time, Earth developed a primitive crust. Continents, these microcontinents, start drifting around. The less dense granitic rock first forming, you know, we didn't have granite in the beginning, but as water mixed in with subducting crust, we formed granite. And this creates microcontinents, as you can see in these pictures here. These are microcontinents. Here, here, all these little continents. And as they start to collide through our first continental drift, they form Laurentia, Rodinia, all these ancient protocontinents. So in the Archean eon, which we'll learn more about later in this unit, microcontinents form and they start to move. In the Proterozoic eon, collisions of these microcontinents create the first supercontinent, Rodinia. Now, as far as our atmosphere goes, we really had no atmosphere until volcanic activity. We pretty much think this is how it happened. Outgassed water vapor, carbon dioxide, carbon monoxide, nitrogen, among other things. And we still were getting extraterrestrial water entering the Earth's atmosphere, accumulating during that bombardment period, as they call it, things colliding with the Earth. You can see in the pictures here how things are bombarding the Earth's surface. And yes, the moon was closer back then. It's moving slowly farther away every year until it reaches a nice balance point. Chemical reactions produced methane and ammonia, which we'll see comes into importance in tomorrow's lesson. And the oceans were greenish in color, kind of bizarre to think about, and they were growing in size as water accumulates. Some evidence for early atmosphere. Chemical analysis of old rocks, very old rocks, and minerals points to an atmosphere very different from today. So we had our outgassing, out the volcanoes. We have comet impacts. And you kind of want to think of it like nowadays how glaciologists can take samples of ice from Antarctica deep below, and they can gather that trapped gas that stuck as the ice was formed, and they can learn about what our atmosphere was like when that ice first formed. Well, geologists can also do similar type experiments with the rock and minerals from the early Earth to learn about what that atmosphere was like. Evidence of early oceans. Sedimentary rocks are usually made on the seafloor. We know that from Unit 2. The oldest sedimentary rocks are dated to about 4 billion years old. So we know around 4 billion years ago, the Earth had primitive oceans. And that's important to understand. They create the first sedimentary rock. In tomorrow's lesson, we'll learn a little bit why these banded iron formations in the right-hand picture here, these red layers stuck within, are so important to understand our early atmosphere and what was happening to make those layers red. And that is it. Quick lesson on the beginning of Earth. I have some videos I want to show you and some homework.